Welcome to All in All. Today we're embarking on, well, an extraordinary journey, really. A deep dive into a concept so rich, so multifaceted, it sort of defies simple categorization. We're
Mhm.
talking about Mercury. Now, for you listening, what's the first thing that springs to mind when you hear that word? Is it that incredibly fast, tiny planet, the one closest to our sun?
Mm.
Or maybe that mesmerizing, shimmering liquid metal, the one famously used in old thermometers?
Right, Quicksilver.
Or maybe even the ancient Roman god,
No.
swift, cunning messenger of the gods.
It's truly fascinating, isn't it, how one single name can conjure such, well, completely diverse images. And that's precisely the core of our exploration today. We've really dug deep, gone through a vast array of sources, everything from cutting-edge astrophysical research and historical texts, right through to modern consumer behavior studies, even some pretty imaginative future proposals.
Wow.
Yeah, all to uncover how this single concept intertwines across cosmic origins, its unique physical properties, its surprising cultural influence, its role in our scientific endeavors, and even its ultimate cosmic future.
So our mission today is what exactly? To kind of distill the essence of it all.
Exactly, to understand its formation, its significance, why it matters, its far-reaching impact on our world, its evolution through time, and its, well, often underestimated practical relevance to us. And we want to do all this while keeping the conversation engaging, hopefully free of impenetrable jargon.
Okay, sounds like a plan. Let's unpack this incredible story then, starting right at the very beginning. We're going to step back billions of years to the violent birth of cosmic Mercury, exploring its mysterious characteristics, and maybe touch on some of those enduring questions that still captivate scientists today. So the prevailing scientific theory, the story of how our solar system came to be, it begins with something truly immense, almost unimaginable in scale. A vast rotating cloud of gas and dust. We're talking about the solar nebula, yeah.
Yeah.
The primordial soup from which, well, everything we know originated.
That's right. I mean, just try to picture this colossal cloud, many, many times larger than our current solar system,
Yeah.
and it's slowly collapsing under its own immense gravity.
Okay.
As it contracted, something called conservation of angular momentum caused it to spin faster and faster, and it flattened out, kind of like pizza dough,
Yeah.
into this thin pancake-like disk. And right there, at its incandescent center, the proto-sun started forming.
And this isn't just guesswork, right? We actually see this happening elsewhere.
Absolutely. It's not just a theoretical construct.
Yeah.
We observe similar processes happening right now in other star-forming regions across the galaxy, nebulae like Orion. That gives us crucial observational evidence for this model. This foundational process is absolutely critical to understanding how all the planets, including tiny Mercury, ultimately took shape.
And from that swirling disk, that pancake of gas and dust, the planets began to coalesce, didn't they? Growing larger and larger. It's often described as a kind of cosmic snowballing.
Yeah, that analogy, while simple, it captures the essence of the process quite well. Within that spinning disk, as temperatures started to cool slightly in specific regions, tiny dust particles and microscopic grains condensed out of the gas, like frost forming on a cold window.
Okay.
These initial microscopic solid particles then began to gently collide and stick together, maybe through electrostatic forces like static cling. And gradually they formed larger and larger bodies we call planetesimals.
Planetesimals.
Wow.
Right. How big are we talking?
Well, they could range from mere centimeters across up to several kilometers in size, little building blocks.
Yeah.
Now, in the hotter inner regions of the solar nebula, particularly close to the forming sun, temperatures were just way too high for volatile compounds, things like water ice, methane ice, or ammonia ice, to condense into solids.
Too hot for ice. Makes sense.
Exactly. So this meant that the terrestrial, or rocky, planets Mercury, Venus, Earth, and Mars formed predominantly from materials that could stay solid at high temperatures. Silicate rock and metallic materials, basically.
So the stuff that makes up rocks and metal.
Precisely. These planetesimals continue to collide and accumulate, or accrete, over millions of years. Their gravity grew, allowing them to sweep up more material, growing into protoplanets, and eventually the full-size planets we recognize today. And as these nascent planets grew, they heated up tremendously.
From all those collisions.
Yes, from the immense energy released during their formation, and also from the decay of radioactive isotopes trapped within them. This heat melted their interiors, allowing the heavier elements, particularly molten metals like iron and nickel, to sink towards their centers. That process is called differentiation. It formed distinct layers, a dense metallic core, a rocky mantle surrounding it, and then a thin outer crust.
Okay, so that's the general recipe for a rocky planet. But you mentioned Mercury is different. Why does it stand out with such an exceptionally large metallic core relative to its overall size? It's not just a small difference, is it? It's like way out of a proportion. That seems like a huge mystery.
It absolutely is, and it's a question that keeps planetary scientists, well, buzzing, with new hypotheses, dedicated missions, the works. The sheer proportion of Mercury's core is just striking. It makes up about 60% of the planet's total mass.
60%.
Yeah, and roughly 85% of its radius. I mean, for comparison, Earth's core is significant, but it's only about 32% of its mass.
Wow, that's a huge difference. So how do we even know this? How do we figure out what's inside?
One of the key clues comes from looking at its density. Scientists can very precisely determine a planet's mass by observing its gravitational effect on other bodies, or especially on spacecraft that fly by.
Ah, like how a probe's path gets bent slightly.
Exactly. Since Mercury has no natural moons, this often involves tracking the incredibly subtle gravitational tug it exerts on passing probes like Mariner 10 or Messenger or Bepi Colombo now. Once we have the mass, and we can calculate the planet's volume from its size, we can derive its density, mass divided by volume.
Okay.
And Mercury's average density is very high, 5.44 grams per cubic centimeter.
How does that compare to Earth?
Well, Earth's bulk density is actually slightly higher, around 5.52 GC meter. But here's the catch. A significant portion of Earth's mass is distributed throughout its much thicker, less dense, rocky mantle and crust. Mercury's high density, despite its smaller overall size, strongly points to an interior that is exceptionally rich in iron and other heavy elements.
So it's packed much more densely with metal.
Precisely.
Yeah.
For instance, Mercury's nickel-iron phase, the metallic part, is estimated to be about 65% of its total mass. Compare that again to Earth's 32.5%.
Okay, 65% metal. That's enormous.
It is. And this striking difference is exactly what scientists are trying to explain. Why so much metal?
And it's not just density giving us clues, is it? I remember reading something about its magnetic field. That implies something specific about the core, too, right?
You're absolutely right. The detection of a global magnetic field around Mercury. This was a discovery initially made by Mariner 10 back in the 70s, and then confirmed in much more detail by the Messenger mission, strongly implies the existence of a substantial liquid iron core.
Liquid, so it's still molten inside.
At least partially, yes.
Yeah.
Much like Earth's magnetic field, Mercury's is generated by the convective motion, the swirling, churning movement of molten iron within its outer core. This process is known as a planetary dynamo.
Like a generator inside the planet.
Kind of, yeah. And this magnetic field, though weaker than Earth's, acts as a crucial shield. It deflects the intense solar wind, protecting the planet's surface from direct bombardment by charged particles from the sun. So the very existence of this magnetic field, coupled with its specific structure, tells us a tremendous amount about the state and composition of Mercury's deep interior. It's powerful evidence that this massive core is indeed still at least partially molten and dynamically active.
That's wild to think about, a churning, molten core inside that tiny, scorching planet. So, okay, we know it has this huge, partially liquid iron core. What are the leading theories for why? You mentioned the sun's magnetic field earlier.
Yes, that's one of the most compelling puzzles in planetary science, and several hypotheses are actively being researched and debated. One leading theory, as you mentioned, suggests that Mercury formed in a region of the very early solar system where the sun's own nascent magnetic field was exceptionally strong.
The young sun had a strong magnetic field.
Likely much stronger and more chaotic than today, yes. This intense magnetic field could have significantly influenced the accumulation of iron during planet formation. You could almost think of it like a cosmic iron filings experiment. The strong magnetic field might have preferentially pulled and concentrated iron-rich materials, the metallic dust grains, into the specific region where Mercury was accreting.
So it's sort of magnetically filtered the building blocks.
That's the idea. This could have resulted in a planet that was disproportionately rich in metallic components right from the outset, thus explaining its unusually large iron core compared to its silicate mantle.
That paints a really vivid picture. But I imagine there are other theories, too, ones that maybe focus more on the chemistry or physics of the nebula itself.
Indeed. Two other prominent hypotheses are often discussed: the metal-silicate physical fractionation hypothesis and the redox hypothesis. They sound a bit technical, but the core ideas are understandable.
Let's try. What's the first one? Fractionation.
Right. The metal-silicate physical fractionation hypothesis suggests that Mercury's high percentage of nickel-iron phase is due to varying proportions of metal, and silicate condensates the solid bits forming out of the gas, accreting in different zones of the solar nebula. This implies some form of physical segregation. Maybe denser metallic particles were somehow more efficiently collected or concentrated in Mercury's formation zone compared to the lighter silicate particles.
Like heavier stuff settling out faster, maybe?
Sort of, or perhaps aerodynamic sorting in the nebula gas, or even, as we just discussed, magnetically controlled segregation of materials very early in the accretion sequence. We actually see some evidence for this kind of separation on a smaller scale in certain types of meteorites, like stony iron meteorites called talicites. They clearly show separate blobs of iron and nickel metal embedded in silicate minerals. So maybe similar processes operated on a much larger planetary scale.
Okay, so basically, different materials condensed or collected differently depending on where you were in the early solar system, and Mercury just happened to be in the iron-rich zone, perhaps helped along by the sun's magnetic field.
That's one way to think about it, yes. A scenario where the initial distribution of building blocks was somehow biased towards metal right where Mercury formed.
And the other one, the redox hypothesis. What does redox mean here?
Redox refers to reduction-oxidation reactions. It's about the chemical environment, specifically how much oxygen was available to react with other elements, especially iron. The redox hypothesis proposes that different oxidation states during Mercury's accretion affected the density of the iron-rich condensates. How? By changing the ratio of elemental metallic iron versus iron oxide, like rust.
Ah, okay, so pure iron versus iron chemically bonded with oxygen.
Exactly. Elemental iron is significantly denser than iron oxide. So if the conditions where Mercury formed favored the formation of more metallic iron, a more reducing environment, less available oxygen, you would pack more mass into a smaller volume, leading to a denser planet overall.
And maybe further out, like where Mars formed, it was more oxidizing, leading to more iron oxide and a less dense planet.
That's the suggestion. The redox state could have varied quite a bit with location and temperature in the early nebula. Both of these hypotheses, fractionation and redox conditions, are being carefully considered. They really highlight the need to accurately estimate the oxidation state and the precise proportion of iron metal versus other elements in the primordial material from which Earth and presumably other inner planets like Mercury accreted.
And it makes perfect sense that iron would be such a key player here, right? I mean, it's not exactly a rare element in the cosmos. You find it everywhere.
Far from rare, you're absolutely right. Iron is actually the sixth most common element in the entire galaxy by mass, and it is the most common metal. So statistically, it's a very, very likely primary component for any rocky planet's core.
It's the default heavy stuff, basically.
Pretty much. And to fully understand how these elements, especially iron, would have partitioned and distributed themselves during planetary formation and, separating into core, mantle, crust, scientists use a powerful framework called Goldschmidt's classification.
Goldschmidt's classification, okay.
Yeah, it categorizes elements based on their chemical affinity, basically what they like to hang out with under the conditions of planetary formation. There are four main groups. Cytophile elements are iron-liking. They tend to dissolve readily in molten iron, and so they concentrate in the metallic cores. Think nickel, cobalt, gold, platinum.
Okay, core lovers.
Then you have chalcophile elements, which are sulfide-liking. They prefer to bond with sulfur. Copper, zinc, lead often fall here.
Sulfide.
Third are the lithophile elements, silicate-liking or oxygen-loving. These tend to remain in the silicate mantle and crust. Elements like silicon itself, magnesium, aluminum, calcium, sodium, potassium, and a lot of oxygen.
So the rock formers.
Essentially, yes. And finally, atmophile elements, which are gas phase-liking. They prefer to be gases or liquids at surface conditions and form the planet's atmosphere and oceans, if present. Hydrogen, helium, nitrogen, carbon, and CO2, the noble gases.
Okay, that makes sense. It helps predict where things end up.
Exactly. This classification helps us predict where an element like iron, strongly siderophile, would prefer to reside within a differentiating planet. And for Mercury, its unique, overly large core strongly suggests conditions during its formation heavily favored the concentration of those siderophiles, the iron-loving elements, right into its core.
So we have these compelling theories, magnetic fields, sorting materials, chemical conditions, but it sounds like despite decades of study and multiple missions, Mariner 10, Messenger, now Bepi Colombo, there are still so many fundamental unknowns about this little planet.
Oh, absolutely.
What are the big, high-priority questions that are still out there for scientists? What keeps them sending probes?
You're absolutely right. Mercury continues to hold many crucial secrets. Despite the incredible progress, especially from the Messenger mission, which orbited Mercury for years, the planetary science community still has many high-priority questions remaining. For instance, we still need to definitively pin down the precise history of Mercury's magnetic field. When did it actually start? How strong was it in the past? How has it evolved over billions of years? What's the exact mechanism generating it today, given its unique core structure?
So the how and when of the dynamo.
Exactly. We also need a much clearer picture of how its surface features and its interior structure uniquely reflect its specific evolutionary path, particularly given that enormous core. How did that affect volcanism, tectonic activity, the crust formation?
Right, cause and effect between the inside and the outside.
Precisely. And then there's the whole question of volatile elements, things like water ice, sodium, potassium. We know Mercury has some, surprisingly, impermanently shadowed craters at its poles and in its thin exosphere. But where did they come from originally? Comets, asteroids, volcanic outgassing. And why are there relatively few compared to Earth or even Mars? What's the full inventory?
The origin of its, well, juices, for want of a better word.
Kind of, yeah. Finally, understanding the complex interplay, the feedback loops, among Mercury's external drivers, especially the intense solar wind and radiation in its magnetosphere, its exosphere, that extremely thin atmosphere, the surface itself, and the deep interior.
Yeah.
It's a major, major challenge. How do all these systems interact?
Wow. So lots still to figure out.
Definitely. These are all active areas of intense research, and current missions like Bepi Colombo are specifically designed with instruments capable of gathering the precise, high-resolution data needed to finally start addressing these profound questions about the solar system's innermost planet.
Okay, speaking of its uniqueness, let's talk about Mercury's orbital dynamics. They really are a dance of extremes, aren't they? It's famous for being the fastest planet zipping around the sun.
Blazingly fast.
Yet it also has one of the slowest spins, one of the longest days in the entire solar system. It's quite the paradox.
It absolutely is.
Yeah.
A year on Mercury, one full orbit around the sun, is incredibly swift. It takes only about 88 Earth days. Zip.
88 days. Our seasons are longer than its year.
Pretty much. This blistering orbital speed is a direct consequence of its close proximity to the sun. It has to move that fast to maintain a stable orbit against the sun's incredibly powerful gravitational pull. Yet its rotation on its axis is remarkably slow. One day on Mercury, from one sunrise to the next, the solar day actually stretches out to about 176 Earth days. But its sidereal day, one rotation relative to the stars, is 58.6 Earth days. Still very slow.
Wait, 58.6 Earth days for one spin. That's incredibly slow. I thought for a long time people believed it was tidally locked, like the moon is to Earth.
That was the prevailing theory for a very long time, yes. Based on early telescopic observations, which were difficult because Mercury is so close to the sun, astronomers believed it was tidally locked in a 1.1 resonance. That would mean one side permanently faced the sun.
Resulting in what? Perpetual scorching heat on one side and eternal frigid darkness on the other?
Exactly. That was the picture for decades. A planet of unimaginable extremes fixed in place.
But then Mariner 10 flew by in the 70s, first spacecraft ever to visit Mercury. And it made a pretty surprising discovery, didn't it? Completely overturned that long-held belief.
It did, yes. And it was a landmark moment in planetary science, a real testament to why we send probes. Mariner 10's data revealed that Mercury is not tidally locked in that simple 1.1 resonance. Instead, it rotates in a fascinating and dynamically stable 3.2 spin-orbit resonance.
3 to 2. What does that mean exactly?
It means that for every 2 orbits Mercury completes around the sun, so 2 Mercurian years, it rotates exactly 3 times on its axis relative to the distant stars.
Okay. 3 spins for every 2 laps.
Precisely. This intricate and stable gravitational dance is the result of the sun's tidal forces acting on Mercury's slightly non-spherical shape over billions of years. It settled into this resonance, which is more stable for its eccentric orbit than a 1.1 lock would be.
And this 3.2 resonance, does it affect the temperatures?
Oh, absolutely. It creates unique and incredibly extreme temperature variations across its surface. Because of this slow rotation and the 3.2 lock, a single solar day, sunrise to sunrise, lasts 176 Earth days. During that long day, surface temperatures can soar to over 400 degrees Celsius, hot enough to melt lead. But during the equally long night, temperatures plummet to below minus 170 Celsius. It also leads to complex patterns of heating, including specific longitudes experiencing the sun directly overhead when Mercury is closest to the sun, perihelion, creating temporary hot poles, not geographic poles, but thermal ones. It's a much more complex and dynamic thermal environment than the simple tidally locked assumption allowed for.
It's the closest planet to the sun. I mean, right there next to that giant furnace. So I always wonder, why isn't it just consumed? Why doesn't the sun's immense gravity just pull it in and swallow it whole? It seems like it should just spiral right in.
That's a very logical question, and it touches on a common misconception about how orbits work. It's not really about being far away, obviously. Mercury is the closest. It's entirely about balance. A delicate equilibrium between its forward speed, its inertia, and the sun's inward gravitational pull.
So speed is the key.
Speed is absolutely the key. Mercury avoids being consumed because its incredible orbital speed. It travels at an average of about 47 kilometers per second. Perfectly balances the sun's immense gravitational pull at that distance.
47 kilometers a second. Wow.
Yeah, it's booking it. Think of it like swinging a ball on a string around your head. The faster you swing it, the more tension there is in the string, the harder it pulls outwards, effectively counteracting the pull of your hand trying to keep it close.
Okay, I can picture that.
Mercury is in a remarkably stable orbit, precisely because it's traveling faster than any other planet in our solar system. It has to travel that fast to stay in orbit so close to the sun. Any object in the early solar system that formed near the sun but didn't have the right combination of speed and distance wouldn't have survived. It either would have collided with the sun or another forming planet, or maybe gotten gravitationally ejected from the solar system altogether.
So the survivors are the ones that found that perfect balance.
Exactly. And what's also fascinating here from a broader perspective is that planets orbiting very close to their stars are actually quite common throughout the galaxy. We've discovered thousands of planets outside our solar system, and many of them orbit incredibly close to their parent stars, sometimes much closer than Mercury is to our sun. These are often called hot Jupiters or hot Neptunes or even hot super-Earths.
So having a planet snuggled up close to its star isn't unusual in the cosmos.
Not at all. In this sense, our solar system, with Mercury in its close orbit, isn't particularly unique. It seems to be a fairly standard outcome of planet formation processes.
Okay, so from the cosmic dance of the planet Mercury, let's shift gears completely. Let's dive into the element itself, liquid mercury. That silvery, shimmering substance, quicksilver, it's captivated humanity for millennia, hasn't it?
It really has.
But this fascinating element also has a surprisingly long and often quite toxic history with humankind.
It certainly does. Mercury, the element, its chemical symbol is Hg. From the Greek hydrogeo, meaning water silver, is actually quite rare in Earth's crust. Its average abundance is only about 0.08 parts per million.
Really? That low? It seems more common somehow.
Well, it concentrates in specific ores. Its primary natural occurrence is in cinnabar, which is mercuric sulfide, HGS. It's often this vivid red mineral found near geologically active regions, hot springs, volcanic areas.
Cinnabar, right, the red pigment.
Exactly. But its truly unique property, the thing that just blew people's minds for centuries, is that it's a liquid at standard room temperature and pressure. It's the only common metal that is.
Yeah, it flows, it beads up, it looks alive almost.
Precisely. That unique liquid state instantly captivated ancient civilizations. They often saw it as mystical, perhaps even a living metal, connected to alchemy and transformation.
But despite its alluring appearance, its sort of magical quality, it seems like ancient civilizations actually had a surprisingly early grasp that this stuff was dangerous.
Yes, they did, often learning the hard way. Both the Mayans, going back as early as 500 BC in places like Guatemala, and certainly the Romans recognized its toxicity, particularly in the context of mining that cinnabar ore.
Mining it was dangerous work.
Extremely. In fact, Roman mercury mines, like the famous ones in Almaden, Spain, which operated for centuries, were essentially penal institutions. Condemned criminals and slaves were sent there, and they faced a grim and tragically brief lifespan.
Because of mercury poisoning?
Directly from mercury poisoning, yes. Mercury is primarily a potent neurotoxin. The miners inhaled mercury vapor released from the ore and suffered severe effects. Symptoms included excruciating joint and muscle pain, a distinctive fine tremor. The Hatter shakes came later, but the effect was known, which could escalate to violent muscular spasms.
Neurological damage.
Severe neurological damage. Extreme mood swings, personality changes, memory loss, hallucinations, and eventually a loss of hearing and restricted vision, that tunnel vision effect. It also caused severe damage to the liver and kidneys. The Roman writer Pliny the Elder described the horrific conditions. The warders were apparently among the first to recognize that the prisoners were highly likely to be poisoned, essentially sparing the need for formal execution sometimes.
God, that's brutal. A death sentence either way.
It's a stark reminder, isn't it, of how humanity has often learned about the dangers of the natural world through incredibly harsh, often exploitative experience.
A truly dark side to its early history. So beyond the inherent danger in mining it, What were some of the other significant ways ancient peoples actually used this fascinating but perilous element?
Well, besides its more direct use in various early forms of medicine, which we can get into, that vivid red cinnabar ore was highly prized as a pigment,
Right, the color.
that brilliant vermilion red. It's been found in Mayan ceremonial sites and tombs dating back to 500 BC, used for painting elaborate murals, pottery, even coating burial goods. And it wasn't just the Mayans. Prehistoric skulls painted with cinnabar have even been discovered in Italy, suggesting maybe ritualistic or funerary uses stretching way back.
And what about medicine? You mentioned that.
Yes, mercury in various forms, including cinnabar, was also incorporated into traditional medicines across many different cultures. It features notably in traditional Chinese medicine and also in Ayurvedic practices from India.
What did they use it for?
Oh, huge range of ailments. Everything from skin conditions and infections to treating internal imbalances, sometimes seen as promoting longevity or spiritual transformation, often processed through complex, sometimes secret, alchemical procedures intended to purify it or reduce its toxicity.
Hmm. Did those processes work?
Well, it's crucial to note that from our modern scientific understanding, the safety and therapeutic basis of these historical uses are now widely questioned, if not entirely discredited. Given our knowledge of mercury's pervasive toxicity, even in small amounts, those ancient applications were likely very dangerous, regardless of the processing methods.
It really sounds like mercury has been deeply intertwined with human history for an incredibly long time. And its uses continued to evolve, didn't they? Right into the modern era, particularly in Western medicine for a while.
Oh, absolutely. Its role shifted, but it remains significant for centuries. Historically, various mercury compounds saw extensive use in Western medicine, really reflecting a time when remedies were often more experimental, based on tradition or observation rather than rigorous testing, and their dangers were much less understood.
So what kind of things was it used for?
Well, calomel, for instance, that's a
Wow.
form of mercury. Chloride was incredibly widely used throughout the 18th and 19th centuries. It was prescribed as a diuretic, a topical disinfectant for wounds, and even quite commonly as a powerful laxative or purgative for all sorts of ailments, believed to cleanse the system.
A mercury laxative. Yikes.
And then there was mercury chloride, or corrosive sublimate, a much more toxic compound. That was actually a common treatment for syphilis for a long time before antibiotics.
Did it work?
Well, it might have had some effect on the bacteria, but here's the terrible irony. The severe symptoms of mercury poisoning itself, things like tremors, excessive salivation, mouth lesions, neurological issues, kidney damage, were often confused with the symptoms of advanced syphilis. So doctors might think the treatment was working, or that the disease was progressing, and they'd continue or even increase the dosage, leading to prolonged and often fatal applications.
That's horrifying. I also remember hearing about something called blue mass. That sounds less alarming, but was it?
Blue mass sounds innocuous, but it was anything but. It was a ubiquitous preparation, particularly popular in the 19th century, available as a pill or sometimes a syrup. Elemental mercury, liquid mercury itself, was the main active ingredient, often accounting for as much as a third of the total mass of the pill.
A third mercury. What was it for?
Pretty much everything. It was prescribed for an absolutely astonishing array of conditions. Constipation, depression, toothache, tuberculosis, influenza, even used in teething powders for infants.
Teething powder. Oh my God.
I know. Just imagine the widespread, insidious mercury poisoning occurring across the population from such common remedies. It's staggering to think about.
So thankfully, we don't use things like calomel or blue mass anymore. But mercury hasn't entirely vanished from medicine, has it? What about dental fillings?
Right, dental amalgam. That's probably the most familiar modern medical-related use for many people. Those silver fillings, which are actually an alloy of mercury, about 50%, mixed with silver, tin, and copper.
Are they safe? There's been controversy.
It's been debated for decades. Tiny amounts of mercury vapor can be released from amalgam fillings, especially during chewing. However, major health organizations worldwide, after reviewing extensive research, have generally concluded that the levels released are very low and not likely to cause adverse health effects in the general population.
But they are being phased out increasingly, right?
They are, yes. Composite resins, the tooth-colored fillings, are becoming much more common due to aesthetic preferences and also ongoing concerns, however small, about mercury exposure and environmental concerns about disposal.
Disposal is an issue.
It is. While dental amalgam isn't considered a major source of overall mercury pollution compared to big industries, it does contribute significantly to mercury found in municipal wastewater and sewer systems. When old fillings are removed or when dental offices dispose of scrap amalgam, estimates vary, but some studies suggest it could be responsible for maybe 5% of total mercury emissions to water in the UK and maybe a third of the mercury load in Canadian sewer systems originating from dental offices. So, proper handling and disposal in dental practices are really important.
Okay. And what about vaccines? There was that whole scare about thiomersal.
Ah, yes. Thimerosal, or thimerosal as it's known in the U.S. That's an ethyl mercury-based preservative that was used in some multi-dose vaccine vials to prevent bacterial contamination.
And the link to autism.
There was widespread speculation and public concern, fueled largely by a now retracted and discredited study claiming a link between thimerosal in vaccines, particularly the MMR vaccine, which actually never contains thimerosal, and autism. However, this hypothesis has been exhaustively investigated. Numerous large-scale, peer-reviewed epidemiological studies conducted across multiple countries involving millions of children have found absolutely no scientific evidence to support any such link.
So the scientific consensus is clear, no link.
The scientific and medical consensus, supported by major health organizations like the WHO, the CDC, the Institute of Medicine, is unequivocal. There's no causal association between thimerosal-containing vaccines and autism spectrum disorders. Vaccines remain one of the safest and most effective public health interventions we have.
But they removed it anyway, didn't they? In some places.
Yes, largely as a precautionary measure and to address public concern, even though the science didn't support the risk. Thimerosal has been removed from or reduced to trace amounts in nearly all routine childhood vaccines in the U.S., Canada, Europe, and many other countries, often replaced by single-dose vials which don't require a preservative.
Okay, good to clarify that. So moving beyond medicine then, mercury's really unique physical and chemical properties made it indispensable in all sorts of industries and niche applications for a very long time, didn't they?
Absolutely. Its unique combination of properties made it incredibly useful, being a dense liquid metal at room temperature and a good electrical conductor. That's a rare combination.
So electrical uses first.
Right. That led to its use in mercury switches. Remember those old thermostats with a little glass bulb containing a drop of mercury that tilted to make or break contact?
Vaguely, yeah. And old light switches sometimes.
Some older silent light switches use them, and tilt switches in things like old fire detectors or industrial controls.
Yeah.
They were simple, reliable, and could handle significant currents, but obviously prone to breaking and spilling.
Okay. And as a liquid for instruments.
Yes. Its properties as a dense liquid with a very consistent and predictable coefficient of thermal expansion made it ideal for precision instruments. Daniel Gabriel Fahrenheit famously invented the accurate mercury in glass thermometer back in the early 18th century. It was a huge improvement in accuracy and range compared to the earlier alcohol-based thermometers. They became the standard for science and medicine for centuries.
But we don't see them much anymore.
No, their use has been declining rapidly since the early 21st century. Due to the environmental and health risks if they break, mercury-containing thermometers and other measuring instruments like blood pressure cuffs, spirometers, are now banned for sale in many countries and largely replaced by digital or other alternatives. It was also a key component in barometers for measuring atmospheric pressure, in diffusion pumps for creating high vacuums in labs, in coulometers for precisely measuring electric charge.
And even in lighthouses. I read that somewhere. That sounds bizarre.
It does, but it's true. In the colossal Fresnel lenses used in many large historic lighthouses, these lenses could weigh several tons. The entire lens assembly often rotated on a bath of liquid mercury.
Why?
The mercury acted as an almost frictionless hydrostatic bearing. It allowed the massive, heavy lens structure to rotate smoothly and effortlessly, propelled by relatively simple clockwork mechanisms, ensuring the beam swept the horizon reliably. An ingenious, if hazardous, piece of engineering.
Wow. Okay. And chemically, what were its big industrial uses, especially in mining? You hear about that a lot.
Chemically, it's been used in the chlor-alkali process for producing chlorine gas and caustic soda, sodium hydroxide, which are vital industrial chemicals. Though mercury cell technology is being phased out globally due to pollution concerns, replaced by membrane cell technology. But historically, and perhaps most infamously from an environmental standpoint, mercury was absolutely crucial in gold and silver mining for centuries. This was through processes involving amalgamation.
Amalgamation, like the dental fillings.
Same principle, different scale. Mercury has the property of readily dissolving or bonding with certain other metals, including gold and silver, to form an amalgam, a sort of metallic paste. In historical mining, particularly the patio process developed in Mexico for silver ore, or later in gold rushes like California's, crushed ore containing tiny particles of gold or silver was mixed with liquid mercury. The mercury would selectively latch onto the precious metals.
Okay, so it collects the gold and silver. Then what?
Then this amalgam paste was collected and heated strongly, usually in a retort. The mercury has a relatively low boiling point, so it would vaporize, leaving behind the purified gold or silver.
But where did the mercury vapor go?
Straight into the atmosphere, mostly, or condensing nearby, polluting soil and water. It's estimated that a staggering 45,000 metric tons, that's 35 million kilograms of mercury used just for placer gold mining during the California gold rush alone, have never been recovered and remain dispersed in the environment, particularly in river sediments.
45,000 tons just in California. That's terrifying.
It's an enormous environmental legacy. While large-scale industrial use of mercury amalgamation largely stopped in developed countries by the 1960s or 70s, it sadly continues today in many small-scale artisanal gold mining operations in developing countries, with devastating health and environmental consequences.
What else? Any other surprising uses?
Well, plenty of others over the years. Mercury compounds were used for preserving wood from rot and insects in anti-fouling paints for ships' hulls to prevent barnacle growth, highly toxic to marine life, sometimes in herbicides. It was essential in developing early photographs. The daguerreotypes in the mid-19th century used mercury vapor to develop the image on a silver-coated plate.
Right. Daguerreotypes.
And then there's the infamous carroting process used in making felt hats, especially from beaver or rabbit fur from the 17th century right up into the mid-20th.
Carroting, like carrots.
The name apparently came from the orangish color the fur sometimes took on. Animal skins were treated with a solution of mercuric nitrate. This toxic chemical process helped the fur fibers mat together more effectively to create high-quality, dense felt.
And this is where Mad as a Hatter comes from.
Exactly. Hat makers, or hatters, were constantly exposed to mercury vapor during this process. They suffered chronic mercury poisoning, leading to pronounced neurological and psychological symptoms, severe tremors, the hatter shakes, slurred speech, irritability, anxiety, paranoia, depression, memory loss, and eventually dementia. The phrase, mad as a hatter, became common slang in the 18th and 19th centuries, directly referencing the very real occupational hazards faced by these workers. Lewis Carroll's Mad Hatter character likely drew inspiration from this well-known phenomena.
Wow. It just permeated so many aspects of life and industry, often with these hidden, terrible costs. I even heard, incredibly, that it was used as a propellant in early space propulsion systems. That sounds both incredibly futuristic and simultaneously really dangerous, given everything we've just discussed.
It seems counterintuitive now, doesn't it? But yes, for a time in the pioneering days of electric space propulsion, mercury was actually a surprisingly key element in that cutting-edge technology.
How did that work?
It was used as the propellant for some of the very first ion engines. NASA's CERT-1, Space Electric Rocket Test 1 mission in 1964, and the longer-duration CERT-2 mission, launched in 1970, successfully demonstrated mercury ion thrusters in space.
Why mercury? What made it good for an ion engine?
It had several advantages on paper. Firstly, its high atomic weight. Heavier ions provide more thrust for a given power level when accelerated electrically. Secondly, it has a relatively low ionization energy, meaning it doesn't take too much energy to knock an electron off and turn it into a positively charged ion that can then be accelerated by electric fields.
Right.
Thirdly, its high density as a liquid allowed for compact storage onboard the spacecraft at room temperature.
So, efficient thrust, easy to ionize, easy to store, sounds good. What went wrong?
Well, significant concerns arose, primarily about its environmental impact during ground testing. Releasing mercury vapor, even in test chambers, was problematic, and there were also worries about its potential performance in space over long missions.
Like what?
The main issue was the potential for mercury propellant to condense on sensitive spacecraft components, solar panels, optical sensors, thermal blankets, especially in the cold vacuum of space during periods when the thruster wasn't firing. This condensation could degrade performance or cause short circuits.
It can freeze on the things.
Exactly. These environmental and operational concerns ultimately led to its replacement. Xenon gas, a heavy noble gas, is now the preferred propellant for almost all modern ion engines used for satellite station keeping and deep space missions.
Why xenon?
Xenon is also heavy, providing good thrust, But it's a noble gas, meaning it's chemically inert, it doesn't react with things.
Yeah.
And while it needs to be stored under pressure as a gas, it doesn't have the same condensation or toxicity issues as mercury. So Mercury had its brief moment in the space age, but it was ultimately superseded.
Okay, so given all these widespread uses, both historical and modern, from medicine to mining to hats to space travel, the health and environmental risks associated with mercury must be incredibly significant and pervasive. It sounds like it's everywhere.
They are, profoundly so. And yes, it's quite pervasive in the environment now due to past and ongoing human activities. It's really important to understand that virtually all humans are exposed to some level of mercury just from the background environment in air, water, soil, and especially through food, like fish. The severity of the health effects depends on several critical factors.
Like what? Is all mercury the same?
No, absolutely not. The type or chemical form of mercury is crucial. Methylmercury, an organic form commonly found in contaminated fish and seafood, is generally considered the most toxic form for humans because it's readily absorbed by the gut and easily crosses the blood-brain barrier in the placenta. Elemental mercury vapor, like from a broken thermometer or industrial emissions, is also very dangerous if inhaled, as it's rapidly absorbed through the lungs into the bloodstream and can reach the brain. Inorganic mercury salts, like those used in old medicines or some industrial processes, are less easily absorbed by the gut, but can still cause severe kidney damage if ingested.
Okay, so the form matters. What else?
The dose, obviously. How much you're exposed to. The duration of exposure. Is it a single acute event or chronic low-level exposure over years? The age and developmental stage of the person exposed. Fetuses, infants, and young children are far more susceptible to the neurotoxic effects of methylmercury because their brains are still developing rapidly. And finally, as we touched on, the route of exposure inhalation of vapor is often the most direct route to the bloodstream and brain, while ingestion is the main route for methylmercury from fish.
So what kind of symptoms can people actually expect? You've mentioned tremors and neurological issues, but what does mercury poisoning look like across that spectrum?
The symptoms vary widely depending on all those factors we just discussed: form, dose, duration, route, age. Let's take chronic low-level exposure to elemental mercury vapor, maybe like those hatters experienced, or workers in certain industries without proper protection. This can lead to insidious, gradually worsening symptoms, things like fatigue, irritability, nervousness, memory loss, difficulty concentrating, insomnia, sometimes vivid dreams, and depression. And then there's that distinctive fine tremor, often called intention tremor, because it gets worse during voluntary movements. It typically begins subtly in the hands and fingers, but can escalate over time to violent muscular spasms, eventually spreading to the eyelids, lips, and tongue, affecting speech and coordination. Kidney damage can also occur with chronic exposure.
Okay, that's chronic. What about acute, high-level exposure, like an industrial accident?
Acute exposure to high concentrations of mercury vapor, maybe from a spill in an enclosed space, even for just a few hours, can be much more dramatic and immediately dangerous. It can cause severe respiratory problems, chest pain, shortness of breath, dyspnea, coughing, inflammation of the lungs, chemical pneumonitis, and potentially pulmonary edema. And alongside the lung issues, you can get profound central nervous system effects quite quickly. Tremors, excitability, sometimes severe psychotic reactions, characterized by delirium, hallucinations, and even suicidal tendencies. It's extremely dangerous.
And you mentioned methylmercury, the kind in fish. Sounds particularly devastating, especially for pregnancy and children. Why is it so bad?
It is devastatingly so, primarily because methylmercury specifically targets and damages the developing central nervous system. In adults, high exposure can cause neurological symptoms like numbness or tingling in the extremities, paresthesia, loss of coordination, ataxia, muscle weakness, tremors, and that severe constriction of the visual field, often described as tunnel vision, potentially leading to blindness. Speech and hearing can also be affected.
And for a fetus?
For a developing fetus exposed to the mother's consumption of contaminated fish, the consequences can be catastrophic and permanent, even if the mother herself shows few or no symptoms. Methylmercury readily crosses the placenta and concentrates in the fetal brain. It can cause severe developmental delays, intellectual disability, cerebral palsy-like symptoms, blindness, deafness, and seizures. The damage is often irreversible. There is currently no effective antidote or treatment for methylmercury poisoning once significant neurological damage has occurred.
We have examples of this happening on a large scale, don't we? Tragic ones.
Yes, unfortunately we do. The most infamous is probably Minamata disease in Japan, starting in the 1950s, caused by industrial discharge of methylmercury into Minamata Bay, which then contaminated the local fish supply. the staple food for the community. Thousands suffered severe neurological damage, and many died. It took years for the cause to be identified and acknowledged. There were also tragic mass poisonings in Iraq in 1971-72. This wasn't industrial pollution, but resulted from people eating seed grain wheat and barley that had been treated with a methylmercury-based fungicide to prevent mold during storage.
Seed grain, but it was meant for planting, not eating.
Exactly. It was imported seed grain intended only for planting. However, it arrived late for the growing season, so some sacks were distributed to rural farming families. The warning labels indicating the grain was treated with poison were apparently in Spanish or English, which most of the rural Iraqi population couldn't read. And the skull and crossbones symbol, while used, was not universally understood as a danger warning in that cultural context at the time.
Oh, that's awful. So people just baked it into bread.
Yes, thinking it was surplus food aid. The result was a massive outbreak of methylmercury poisoning. Official figures reported 6,530 people hospitalized and 459 deaths, though the true numbers might have been higher. It was a devastating public health catastrophe caused by a tragic failure of communication and regulation.
And I think you mentioned a similar case in the U.S., too.
A smaller but equally tragic series of cases occurred in New Mexico in 1969-70. A family raised pigs and fed them seed grain that had been treated with the same type of methylmercury fungicide, grain that had been spilled or left over. They then slaughtered and ate one of the contaminated pigs over several months.
Oh.
3 of the children became severely ill with classic symptoms of methylmercury poisoning. 2 of the younger children tragically died, and the eldest surviving child suffered permanent visual impairment and neurological damage. This incident, along with the events in Iraq, really highlighted the extreme danger of methylmercury entering the food chain and led to much stricter regulations on its use in agriculture globally. It's just chilling to think how long it took humanity to truly grasp the insidious danger of this substance, despite centuries of exposure and countless tragic lessons learned.
So it's really clear this isn't just some historical problem confined to, Mad Hatters or ancient Roman mines. It's an ongoing, major global environmental concern. Where does most of the pollution come from today?
Yes, it's absolutely a current and global issue. While some historical sources, like maybe improperly disposed thermometers or, as we discussed, dental amalgam flushed down drains, do contribute small amounts locally, the vast majority estimates suggest around 99% of global anthropogenic, that means human-caused, mercury pollution entering the environment today comes from large-scale industrial activities.
Like what? What are the biggest culprits?
Chief among these globally is artisanal and small-scale gold mining, which we talked about. That releases huge amounts directly into local environments, often with devastating health impacts on the miners and communities. But beyond that, a major source of atmospheric mercury emissions is the burning of coal, especially in coal-fired power plants for electricity generation. Coal naturally contains trace amounts of mercury, and when it's burned, that mercury is released as vapor into the atmosphere.
So power generation is a big one.
A very big one globally, yes. Other significant industrial sources include certain types of non-ferrous metal production, like smelting zinc, copper, lead, cement production. Mercury can be present in the raw materials like limestone, and waste incineration if mercury-containing products aren't properly removed beforehand.
What about hydroelectric dams? I heard they can be a source too, which seems odd.
It does seem counterintuitive, because hydropower is often seen as clean energy. But building large dams and creating reservoirs can lead to mercury problems. When vast areas of land are flooded, the organic matter in the submerged soils decomposes under low oxygen conditions. Bacteria in this environment can convert naturally occurring inorganic mercury, which might have been relatively harmless locked in the soil, into the much more toxic methylmercury.
And that gets into the water.
Yes, it gets released from the sediments into the reservoir water, and then it can enter the aquatic food chain. Fish living in newly created reservoirs often show significantly elevated levels of methylmercury for decades after the dam is built. So it's an indirect consequence, but a documented one.
So the mercury gets released into the air from things like coal plants or into water from mining or dams. What happens then?
Once released into the air, mercury vapor can travel long distances on wind currents, potentially circling the globe, before it eventually deposits back onto land or water surfaces, often far from the original source. This makes it a transboundary pollution problem.
Right, so pollution from one country can affect another.
Exactly. And once it deposits into aquatic environments, lakes, rivers, oceans, that's where the real trouble with methylmercury begins. As I mentioned, certain bacteria in low-oxygen sediments can convert this deposited inorganic mercury into methylmercury. This methylmercury is then readily taken up by microscopic organisms at the bottom of the food chain, like algae and plankton. Then small fish eat the plankton, bigger fish eat the small fish, and so on. At each step up the food chain, the methylmercury becomes more concentrated. This process is called biomagnification.
So it builds up in the animals higher up.
Dramatically. Long-lived predatory fish at the top of the aquatic food chain, like shark, swordfish, king mackerel, pilefish, and even some larger tuna species, can accumulate levels of methylmercury, thousands or even millions of times higher than the concentration in the surrounding water.
And that's why there are advisories about eating certain types of fish, especially for pregnant women.
Precisely. Those advisories are based on the risk of exposure to potentially harmful levels of methylmercury that have biomagnified up the food chain. It poses a direct threat to human health through consumption.
Okay. So what are we actually doing about this pervasive global problem now? Are there effective regulations and safe practices in place or being put in place to try and mitigate these risks?
Yes, thankfully there are significant global and national efforts underway, although it's a complex and ongoing challenge. Internationally, the most important framework is the Minamata Convention on Mercury. It was adopted in 2013 and entered into force in 2017, named after the Japanese city that suffered that devastating poisoning event.
What does the Minamata Convention do?
Its main goal is to protect human health and the environment from anthropogenic emissions and releases of mercury and mercury compounds. It requires signatory countries, and most countries are now parties to it, to take a range of actions. These include phasing out the manufacture, import, and export of many mercury-containing products by specific deadlines, like batteries, switches, certain lamps, cosmetics, pesticides, and measuring devices like thermometers and barometers. It also mandates controls on mercury emissions from major industrial sources like coal plants and smelters, requires national action plans for reducing mercury use in artisanal gold mining, and addresses issues like mercury storage and waste management.
So it's a comprehensive global treaty.
It aims to be, yes. Implementation takes time and resources, especially in developing countries, but it provides a crucial legal framework and political impetus for global action. Domestically, many countries and regions had already implemented regulations before Minamata or have gone further since. For instance, the European Union and many U.S. states have implemented bans on the manufacture and sale of new mercury-containing instruments, like thermometers and sphygmomanometers, well ahead of the convention's deadlines.
What about mercury waste? Is it treated specially?
Yes. Mercury waste is widely classified as hazardous waste in most developed countries. In some places, like the U.S. under the Resource Conservation and Recovery Act, RCRA, certain common mercury-containing items like thermostats, lamps, and batteries might be managed under streamlined regulations as universal waste.
Universal waste, what does that mean?
It's a specific category designed to make it easier for businesses and consumers to collect and recycle certain common types of hazardous waste, rather than having them end up in regular trash and landfills where the mercury could eventually be released. The regulations are generally less stringent than for fully regulated hazardous waste, but they still mandate proper handling, storage, labeling, and transport to designated recycling or disposal facilities.
Does that encourage recycling?
That's the goal, to encourage proper disposal and recycling by making it slightly less burdensome while still ensuring environmental protection. However, household hazardous waste, including items containing mercury, is often exempt from these regulations, which remains a challenge for capturing mercury from residential sources. Some states or local jurisdictions in the U.S. have gone further, implementing even more stringent regulations, with some outright banning all mercury-containing waste from landfills, regardless of whether it's from a business or a household.
So progress is being made, but it sounds like the legacy of past pollution and ongoing emissions from some big industries mean that managing mercury's environmental impact is still a persistent, really critical challenge for us globally.
Absolutely. It's a long-term commitment requiring continued vigilance, technological innovation, international cooperation, and effective enforcement of regulations.
Okay, this brings us to a truly fascinating intersection now. Mercury in human culture. Moving away from the physical planet and the chemical element, let's explore its role in our beliefs, its ancient mythological roots, and its surprisingly tangible influence on modern life, even consumer behavior. Let's start with the Roman god himself, Mercury.
Right, the god Mercury. Known as Hermes in the earlier Greek mythology, from whom the Romans largely adapted him. He's an exceptionally rich and multifaceted figure in the Roman pantheon.
He wasn't just the messenger god, was he?
Oh, far from it. He was a major deity, one of the 12 De Consentus, the Council of Principal Gods, and he embodied an absolutely astonishing array of domains. Yes, he was the swift messenger of the gods, particularly Jupiter, but he was also the god of financial gain, commerce, merchants, eloquence, poetry, messages, communication in general.
Okay, busy guy.
Very busy. Also the god of travelers, boundaries, both physical and metaphorical, luck, trickery, and thieves. He had a mischievous side. And crucially, he also played a vital role as the psychopomp,
Psychopomp. What's that?
the guide of souls. It was Mercury, or Hermes, who guided the spirits of the dead down to the underworld, to the realm of Pluto. So he navigated the boundary between life and death.
Wow. Messenger, commerce, luck, thieves, guide to the underworld. He really covered a lot of ground.
He really did. His iconic symbol, which most people recognize as the caduceus.
The staff with the wings and the two snakes wrapped around it, often confused with the rod of Asclepius, the symbol of medicine.
Exactly. The caduceus, Mercury's staff, represents far more than just medicine, which is technically Asclepius's single snake rod. The two intertwined snakes on the caduceus are often interpreted as symbolizing duality, negotiation, mediation, diplomacy, the bringing together of opposites. The wings represent swiftness, communication across realms. The staff itself can symbolize power, authority, or the axis mundi connecting heaven and earth. It's seen as representing transformation, balance, and even the rhythm of time, reflecting his role as a bridge between different worlds and states of being.
He sounds like the ultimate multitasker then, a kind of celestial go-between connecting different worlds, different concepts, different people.
Precisely. That's a great way to put it. Metaphysically, or in more esoteric traditions that draw on mythology, Mercury is often seen as a supreme mediator. He bridges not just the divine and human realms, but also encourages a balance within ourselves. A balance between intellect and intuition, between logic and emotion, between the conscious mind and the subconscious. He's often described metaphorically as an inner messenger, the aspect of our psyche that helps us communicate with ourselves, guides us through transitions, and helps translate raw experience into understanding and wisdom, or helps turn abstract understanding into concrete action in the world.
That's a really interesting psychological interpretation. Did the ancients think about him in those abstract terms?
Well, maybe not in modern psychological jargon, but the core concepts were there. This idea of him as a mediator and guide has deep ancient roots. We have evidence that the ancient Greeks were keenly interested in planetary motions and their perceived influence on earthly affairs. For example, there's an early Greek relief sculpture dating back to maybe the 4th century BCE that depicts Hermes, Mercury, associated with the constellation of Leo, the lion. This highlights their tracking of planets and associating them with zodiacal signs very early on.
And what about his physical presence in the ancient world?
Statues or shrines dedicated to Mercury, often called herms in Greece, which were typically pillars topped with his head and featuring male genitalia, were traditionally placed at boundaries, city gates, and especially at crossroads.
Crossroads, why there?
Crossroads were seen as places of transition, decision, potential danger, but also opportunity. Placing Mercury there symbolized his protection over travelers and merchants who frequented these routes. It signified his domain over movement, commerce, and communication happening at these meeting points. It also reflected his crossing know-how, his perceived ability to help people navigate transitions successfully, whether those were physical journeys or more abstract changes in fortune or life stages. He was the god you might pray to for a safe journey or a profitable business deal.
Okay, now here's where it gets really interesting for me. Connecting these ancient beliefs and this mythological figure to very modern, tangible life. The whole Mercury retrograde phenomenon. This seems to have absolutely exploded in popular culture, particularly maybe in the last couple of decades. You hear about it constantly.
It definitely has. It's become a pervasive meme online, a common topic of conversation, and for many people, a genuine point of anxiety, or at least caution.
So what is it actually, astronomically? Is Mercury really going backward?
No, not physically. The Mercury retrograde phase is purely an optical illusion, an effective perspective from Earth. Because Mercury orbits the Sun much faster than Earth does, roughly 4 times faster, it's an 88-day year versus our 365, and because our orbits are elliptical and tilted relative to each other, there are periods when Earth, in its slower orbit, overtakes Mercury. From our vantage point on Earth during these periods, Mercury appears to slow down, stop, and move backward, westward, against the background stars for a few weeks.
Like when you pass a slower car on the highway, and for a moment it looks like it's going backward relative to you.
That's a perfect analogy. It's exactly the same principle. Mercury never actually reverses its orbital direction. It happens 3 or 4 times every year, each retrograde period lasting about 3 weeks.
Okay, so it's an illusion. But in popular astrology, this period has become totally infamous, hasn't it, for causing chaos?
Infamous is the word. In popular astrology, which assigns meanings and influences to planetary movements, Mercury rules communication, technology, travel, contracts, intellect, information flow. So when the planet appears to go backward, astrologers interpret this as a time when all those areas of life are likely to go haywire.
Haywire how?
You hear warnings about communication breakdowns, misunderstandings, arguments, technology malfunctions, computers crashing, emails getting lost, phones breaking, travel delays, cancellations, lost luggage, contracts falling through, negotiations stalling, mistakes in paperwork, general confusion and frustration.
So the advice is basically don't do anything important.
Pretty much. Astrologers widely advise people against making major decisions, signing important contracts, launching new projects, buying electronics or cars, or even having crucial conversations during Mercury retrograde. The common refrain is that things just go wrong, plans get disrupted, and efforts are likely to be frustrated or need revision later.
And astonishingly, these popular beliefs, this astrological folklore, it seems to actually influence people's real-world behavior, even in ways that you can measure, ways that impact the economy. It's not just an anecdotal quirk, is it?
That's perhaps one of the most surprising findings to come out of recent, rigorous academic research looking into this phenomenon. Studies using actual consumer purchasing data have observed a statistically significant decrease in consumer purchases, particularly for large discretionary items like electronics or appliances, during Mercury retrograde phase as compared to other times.
Really? People actually hold off buying things because of it?
The data suggests they do, yes. It indicates that a non-trivial number of consumers are genuinely wary of this astrological phenomenon and adjust their spending habits accordingly, perhaps fearing the product will be faulty or the decision ill-fated.
That's amazing. But what about bigger picture stuff, like financial markets?
That's even more astonishing. There's research published in peer-reviewed finance journals like the Journal of Behavioral Finance that shows market returns are measurably lower during Mercury retrograde periods compared to other times of the year.
Lower market returns? How much lower?
One prominent study found an average difference equivalent to about 3.22% annually, meaning if you only invested when Mercury was not retrograde, historically your returns might have been significantly higher. They call it the Mercury effect in financial markets.
Wow, 3.22% is not insignificant in finance. How can that be? Is Mercury actually affecting the stock market?
Well, the researchers are very clear. They're not suggesting the planet itself exerts any physical influence. Instead, the effect seems to be consistent with the idea that investors' shared beliefs, moods, or perhaps their subconscious caution and risk aversion, influenced by this widespread cultural belief, translate into tangible market shifts. Maybe slightly less buying activity, slightly more selling pressure, enough to measurably dampen returns during those specific periods.
So it's a kind of self-fulfilling prophecy driven by collective psychology.
That appears to be the most plausible explanation from a behavioral finance perspective. It demonstrates how powerful, culturally ingrained narratives and shared beliefs can be, even in supposedly rational domains like financial markets.
That really paints a picture of the incredible power of shared belief systems. And is there any pattern to where this effect is stronger?
Yes, and this is perhaps the most fascinating piece of the puzzle. The research shows that this Mercury effect on market returns is demonstrably stronger in countries with a greater cultural affinity for or historical connection to ancient Greek culture.
How do they measure that?
They use proxies, like analyzing Google search volumes within different countries for terms like ancient Greece, mythology, Hermes, and related concepts. They found that in countries where these terms are searched more frequently, indicating a higher level of cultural awareness or interest in Greco-Roman heritage, the negative market anomaly during Mercury retrograde tends to be more pronounced.
So places with deeper roots in classical traditions feel it more.
That seems to be the correlation, yes. For example, countries with strong historical ties to classical education, or where Greco-Roman mythology is more embedded in the cultural background, tend to show a stronger market reaction. The study also notes that Christianity, with its deep historical and philosophical entanglement with ancient Greek culture through philosophy, early church fathers, Renaissance humanism, etc., is one of the major cultural streams that has likely influenced and perpetuated these types of beliefs, consciously or unconsciously, through various intellectual and folk traditions over centuries.
That's incredible. It suggests that the cultural transmission of these ancient ideas, maybe often subconsciously, continues to shape modern decision-making and collective behavior on a measurable scale.
It really does seem to point in that direction. It's a stunning example of cultural persistence.
This also really highlights a significant contrast, doesn't it? Between astrology, which has these incredibly deep cultural and historical roots and clearly still influences millions of people, and modern astronomy, which operates on a completely different basis, empirical observation, physical laws, the scientific method.
Absolutely. It's a fundamental divergence. While astrology, with its ancient origins, its complex systems of symbolism, and its focus on personal meaning and cosmic influence, continues to hold appeal for many people, and surveys show belief is sometimes higher in countries with perhaps lower levels of scientific development or where traditional beliefs remain very strong. Modern astronomy explicitly parted ways with mythological and astrological planetary theories centuries ago, especially after the scientific revolution.
Right, with Copernicus, Kepler, Galileo, Newton.
Exactly. Their work established the physical laws governing planetary motion, gravity, celestial mechanics, providing a purely scientific mathematical framework for understanding the solar system that does not incorporate or validate astrological interpretations of planetary influence on human affairs. It's a clear epistemological distinction, two different ways of knowing or interpreting the cosmos.
And do we know if belief in astrology is declining with more science education?
It's a mixed picture, but data from places like the U.S. does show a trend. Surveys by organizations like the National Science Foundation indicate that the proportion of people who consider astrology not at all scientific has actually increased over time, maybe from around 50% in the late 1970s to over 60% by the 2010s. Yet despite this scientific skepticism, its enduring popular appeal, fueled by media, the internet, and perhaps a human desire for meaning and guidance, underscores just how deeply these cultural narratives can embed themselves in the collective consciousness, sometimes operating independently of scientific validation.
But even with that scientific separation, putting astrology aside for a moment, there's maybe a different way to look at these retrograde periods, a more metaphysical or spiritual angle perhaps, not necessarily about chaos, but something else.
Indeed there is. From a more metaphysical or contemporary spiritual perspective, these retrograde periods, not just Mercury's, but other planets too, are often not viewed primarily as times of misfortune or external disruption to be feared.
How are they viewed then?
They're often framed, more positively, as powerful opportunities for internal work, for reflection, reassessment, review, and introspection. The prefix re becomes key. Rethink, revise, reconsider, repair, reconnect, release.
So turn inward instead of blaming the planet.
Exactly. It's often suggested as an invitation from the cosmos to pause, slow down the usual outward pace, and reconsider things. How are we communicating? Are our messages being received clearly? How are we processing information internally? Are our thought patterns serving us? This period, from this viewpoint, is suggested as an ideal time for activities like journaling, meditating, clearing out clutter, both physical and mental, revisiting old projects or ideas with fresh eyes, reconnecting with past contacts, or clarifying intentions before moving forward again once the planet appears to go direct.
So it's reframed as a time for productive inner maintenance almost.
Precisely. By turning inward and using the period for conscious reflection, individuals might gain valuable insights about their communication habits, their decision-making processes, their relationships, and their overall personal growth. It shifts the focus from sharing external chaos to embracing an opportunity for deeper self-awareness and course correction, a chance to integrate lessons learned.
This brings us then to the future of Mercury. And there are really two aspects here, aren't there? A potential future involving human exploration, however challenging, and then its ultimate, much more distant, dramatic cosmic destiny. Let's start with getting there. Sending a spacecraft to orbit Mercury sounds like an incredibly difficult engineering feat. Maybe one of the hardest destinations to reach in the solar system, ironically because it's so close to the sun.
It absolutely presents some of the most significant engineering challenges in robotic space exploration. You hit the nail on the head. Its extreme proximity to the sun is the main problem. Spacecraft going to Mercury face absolutely intense heat and radiation loads, far, far more than missions going to Mars or the outer planet.
How much hotter are we talking?
Well, the solar intensity at Mercury is roughly 7 times stronger than it is at Earth on average, and can be up to 11 times stronger when Mercury is at its closest point to the sun. This necessitates incredibly sophisticated thermal control systems.
Like what kind of systems? Just paint.
Oh, much more than paint. We're talking multi-layered heat shields made of advanced ceramics and insulation materials, highly reflective mirror-like coatings, often using materials like optical solar reflectors, OSRs, are crucial to bounce away as much sunlight as possible. You saw these prominently on the Bepicolombo mission's Mercury Magnetospheric Orbiter, MIO, those big reflective surfaces. Sensitive instruments have to be carefully positioned, often on the shaded side of the spacecraft or behind radiators. Designing electronics, solar panels, and propulsion systems that can simply survive, let alone operate reliably under these scorching, high radiation conditions for years, is a massive, massive undertaking.
I always thought, getting to Mercury would be relatively straightforward, maybe a quick shot inwards towards the sun since it's the closest planet much of the time. But missions like Bepi-Colombo take years to get there. Why is that? It seems completely counterintuitive.
It absolutely does seem counterintuitive, and it's a really common point of confusion for people. Bepi-Colombo, for example, launched in 2018 and only arrived in orbit around Mercury in late 2025. That's a 7-year journey.
7 years to get to the nearby planet.
Exactly. It's not because Mercury is far from Earth in terms of distance, as you said. It's often closer to us than Mars is. The incredible challenge lies in getting a spacecraft to slow down enough relative to the Sun to actually be captured by Mercury's relatively weak gravitational pull.
Why is slowing down so hard?
Because to get to Mercury from Earth, you have to lose a tremendous amount of orbital energy. You're essentially falling deeper into the Sun's powerful gravity well. If you just pointed a rocket towards Mercury and fired, you'd arrive there going incredibly fast, far too fast for Mercury's gravity to capture you. You just whip right past it and continue falling towards the Sun.
So you need brakes, really powerful brakes.
Exactly. But using conventional rockets to apply those brakes to shed all that orbital velocity would require an absolutely enormous amount of propellant. So much propellant that the spacecraft would become prohibitively heavy and expensive to launch.
Ah, okay. So how did they do it then, if not with giant retro rockets?
This is where the cleverness of orbital mechanics comes in, using the concept of swing-by maneuvers, also known as gravitational assists.
Using other planets' gravity.
Precisely. A swing-by uses a planet's gravity and orbital motion to adjust a spacecraft's speed and trajectory relative to the Sun, without expending precious onboard propellants. It's like cosmic billiard balls. For Mercury missions, this usually means performing multiple flybys of planets like Earth and Venus on the way in, and sometimes even multiple flybys of Mercury itself once you get closer. Each flyby can be carefully timed and targeted to use the planet's gravity to steal some of the spacecraft's orbital energy, effectively braking it relative to the Sun.
So it's a slow, multi-step braking process using planets.
Exactly. This technique is incredibly propellant efficient, which is essential, but it requires very precise navigation and long waiting periods between flybys for the planets to get into the right alignment in their orbits. You have to wait for the right opportunity for each gravitational assist. Bepi-Colombo, for instance, performed one Earth flyby shortly after launch, then 2 Venus flybys over the next couple of years, and then it needed 6 separate Mercury flybys, spread out over several more years, before it had slowed down enough to finally be captured into orbit around Mercury.
6 Mercury flybys just to get into orbit. Wow.
Yeah. These complex sequences of gravitational assists are what account for the extended mission durations. They make the journey a complex cosmic ballet, carefully choreographed over many years, rather than a quick dash.
Okay, that makes sense now why it takes so long. So once Bepi-Colombo finally gets there and settles into its 2 orbits, what exactly are scientists hoping to learn from this dual spacecraft mission? What are its key scientific objectives?
Bepi-Colombo has some incredibly ambitious scientific objectives, really building on what Mariner 10 glimpsed and Messenger mapped in detail. And having 2 orbiters working together is key. There's the Mercury Planetary Orbiter, MPO, built by the European Space Agency, ESA, which is in a low orbit to study Mercury's surface and interior composition in detail. And then there's the Mercury Magnetospheric Orbiter, MIO, built by the Japan Aerospace Exploration Agency, JAS, which is in a higher, more elliptical orbit designed specifically to investigate Mercury's magnetic field, its magnetosphere, the region dominated by that field, and its interaction with the solar wind.
So they look at different things simultaneously.
Exactly. They provide complementary data. Together, their primary goals are 2. 1. Study Mercury's interior structure and composition. By making extremely precise measurements of its gravitational field, how it varies slightly from place to place, and its magnetic field, scientists hope to gain crucial new insights into the size, the state, is the outer core fully liquid,
Mm.
partially solid, and the exact composition of that massive metallic core. And they want to understand how that unique core structure drives the planet's internal dynamics and magnetic field generation.
Okay, unlock the core mystery.
That's a big one, yes. 2. Investigate the surface geology and composition. MPO has advanced cameras and spectrometers to map the surface in unprecedented detail, identify different rock types and mineral compositions, study volcanic features, impact craters, and tectonic structures, like the scarps formed as the planet cooled and shrank. This helps piece together Mercury's geological history. 3. Observe its thin sodium atmosphere, or more accurately, its exosphere. Both orbiters carry instruments to study this tenuous envelope of gas. They want to understand its exact composition. It's mostly sodium, potassium, calcium, magnesium sputtered off the surface. How it's generated by solar wind bombardment, micrometeoroid impacts, maybe outgassing. How it varies over time and location, and how it interacts with the solar wind and the planet's magnetic field and surface.
It sounds like an atmosphere, but it's almost a vacuum, right?
Extremely thin, yes. The atoms are so spread out they rarely collide with each other. That's why it's called an exosphere. 4. Analyze the magnetic field and magnetosphere. MIO's main job is to fly through different parts of the magnetosphere, measuring the magnetic field strength and direction, plasma particles, waves, and how the whole system responds to the constantly changing solar wind conditions. This will give us the best understanding yet of Mercury's unique mini-magnetosphere. 5. Test Einstein's theory of general relativity. Because Mercury orbits so close to the Sun's immense gravity, its orbit provides a natural laboratory for testing subtle predictions of general relativity with extremely high precision by tracking the spacecraft's position. And finally, 6. Investigate the solar system's innermost dust environment. The region very close to the Sun is largely unexplored in terms of interplanetary dust. Bepicolombo carries dust detectors to provide valuable data on the distribution, origin, comets, asteroids, collisions, and characteristics of these tiny particles, which could tell us a lot about processes happening near the Sun.
Wow, that's a huge list of objectives. A really comprehensive mission.
It really is.
Yeah.
By having those two satellites in different complementary orbits, they can simultaneously observe the planet and its surrounding space environment, gathering a much more complete picture than any single orbiter could. It promises to revolutionize our understanding of this enigmatic innermost planet.
And this research, particularly understanding Mercury's magnetic field and how it interacts with the solar wind, it has implications far beyond just Mercury itself, doesn't it? I remember you mentioning it connects to the much broader quant of life beyond Earth. How so?
It absolutely does. Understanding Mercury's magnetic field isn't just an academic exercise in planetary science. It's incredibly significant for the broader, overarching search for life beyond Earth, for understanding planetary habitability in general.
Why are magnetic fields so important for habitability?
Planetary magnetic fields, like Earth's, are thought to play a crucial role in protecting a planet's atmosphere and surface from the harsh effects of its star's stellar wind and high-energy cosmic radiation. The stellar wind is a constant stream of charged particles flowing out from a star. Without a strong magnetic field to deflect most of these particles, the stellar wind can, over millions or billions of years, gradually strip away a planet's atmosphere, especially for planets orbiting closer to their star or around more active stars.
Like what might have happened to Mars?
Exactly. Mars lost its global magnetic field early in its history, and many scientists believe this was a key factor in allowing the solar wind to erode its once thicker atmosphere, leading to the cold, dry, low-pressure environment we see today, making the surface much less habitable. This atmospheric stripping process can also allow more harmful radiation, like energetic particles and UV rays, to reach the surface, potentially sterilizing it or making it very difficult for life as we know it to survive or evolve.
So studying Mercury's mini-magnetosphere helps us understand this protection mechanism.
Precisely. Mercury provides a unique test case. It has a magnetic field, albeit weaker than Earth's, but it's extremely close to the Sun and subject to a much more intense solar wind. Studying how its magnetosphere holds up, how it interacts with the solar wind, how much protection it actually offers the surface, and the exosphere this knowledge gained from Mercury will be vital for assessing the potential habitability of exoplanets we discover orbiting other stars.
Especially exoplanets close to their stars?
Yes, particularly those rocky exoplanets found in the habitable zones of their stars, where liquid water could potentially exist. We need to know if having a magnetic field is a necessary condition for maintaining an atmosphere and surface water over geological timescales. A strong, stable magnetic field is increasingly considered a key factor, perhaps even a prerequisite, for a planet to be considered potentially habitable in the long term. So Mercury, in a way, helps us refine our search criteria for life elsewhere in the universe. Hashtag 4.2, a human future on Mercury.
Okay, so with all this exploration, robotic for now, it inevitably sparks the imagination. Could Mercury ever be a future home for humanity? Could people actually live there? I've even seen some, well, maybe slightly fringe discussions suggesting it might somehow be better than Mars for colonization, which sounds utterly wild given its extreme environment of scorching heat and deep cold.
It's definitely an intriguing thought experiment, pushing the boundaries of future possibilities. And some of our sources, particularly those exploring more speculative scenarios, certainly delve into fascinating hypothetical designs for what human life could be like on such an extreme world. While much of our deep dive focuses on the established science, these proposals are interesting because they force us to think about adaptation. And yes, some arguments have been made, perhaps provocatively, suggesting Mercury might offer advantages over Mars for future large-scale human expansion.
Advantages? Like what? It seems so much harsher.
The main arguments usually center on two things. Firstly, the absolutely enormous amount of solar energy available there, which could theoretically power vast industrial operations or settlements if harnessed effectively. Secondly, the surprising discovery of water ice and other volatile compounds trapped in permanently shadowed craters near Mercury's poles. These could potentially provide resources like water and maybe even rocket fuel components, perhaps more accessibly than on Mars, where water ice is mostly subsurface or requires more processing.
Okay, energy and maybe water at the poles. But living there, the conditions?
So living there would require radical adaptation, no question. Settlements would almost certainly have to be built underground, perhaps tunneling into crater walls, or located entirely within those permanently shadowed polar craters where temperatures remain relatively stable and extremely cold, shielding inhabitants from the direct solar radiation and heat extremes found elsewhere on the planet.
Like living in a giant freezer at the poles or deep underground.
Essentially, yes. One source we looked at imagines a hypothetical colony of Metropolis, founded notionally in 1991, in its timeline, within the Prokofiev crater near Mercury's North Pole, taking advantage of that permanent shadow. And for future colonists living in such confined, extreme environments, their entire relationship with time would have to be fundamentally different from ours on Earth. So much so that it would likely necessitate its own completely different way of tracking days and cycles, maybe manifest in a specialized Mercurian calendar.
A Mercurian calendar, how would that work?
Well, one proposed system uses a standard 24-hour period called a date as its fundamental unit, similar to our day, providing a familiar rhythm for daily life within the settlements, independent of the sun's position outside. Then, 8 of these dates would form a week, and 22 of these weeks would make up one cycle, which roughly corresponds to Mercury's 88 Earth day orbital period, its year.
Okay, so date, week, cycle. What about keeping it accurate?
To keep this calendar precisely aligned with Mercury's complex orbital and rotational dynamics, remember that 3.2 resonance, there would need to be adjustments, like adding leap hours, perhaps on odd-numbered cycles. The key point is that for colonists living underground or in those polar craters, their experience of time would often be decoupled from the actual surface day-night cycle happening outside. Their internal clocks, work schedules, social rhythms would likely be regulated by something like a polar standard time, governing life within the relatively stable, artificially lit environments, regardless of whether it was blazing day or freezing night on the surface miles away.
So if they're living underground or at the poles, they wouldn't really experience seasons in the way we do. How would daily life and maybe even cultural things like holiday traditions adapt to those truly radical extremes of light and dark happening outside?
You're absolutely right. Mercury has virtually no axial tilt. Its axis is almost perfectly perpendicular to its orbital plane, unlike Earth's 23.5-degree tilt. So it doesn't experience Earth-like seasons caused by varying directives of sunlight on different hemispheres throughout the year.
No summer or winter tilt.
Exactly. Instead, its seasons, which you can call them that, are defined entirely by that incredibly extreme day-night cycle, which, as we discussed, is a consequence of its unique 3.2 spin-orbit resonance. Remember, the Mercurian solar day, the period from one sunrise to the next, at a given spot on the equator, lasts for 176 Earth days. That's roughly 6 months of continuous daylight, followed by 6 months of continuous night.
6 months of sun, 6 months of darkness. Wow.
And those transitions are incredibly long, too. Sunsets and sunrises, from the first appearance of the sun's disk to its full setting or rising, are described in these hypothetical scenarios as lasting an astonishing 384 Earth hours. That's 16 Earth days.
16 days for a sunrise.
Yeah, and they're imagined as having perhaps a deep blue hue initially, while the daytime sky, when you're not looking directly at the sun, might range from pinkish to yellow, or just blinding white glare if you face the sun.
So how would holidays work? You couldn't have a Christmas day.
No, holidays and cultural celebrations would have to adapt dramatically to these vast cycles of light and dark, heat and cold. One source speculates about potential traditions. Maybe a major celebration called morning solstice, marking the symbolic end of the perilous long night, just before the dawn begins its slow creep across the landscape. A time of relief and preparation. Or perhaps evening solstice, celebrating the coming return of darkness, and maybe the symbolic life-giving rains, perhaps referring to resource replenishment cycles within the colony, at the end of the grueling long day, just before dusk fully sets in. The long dawn and dusk periods themselves, lasting over 2 weeks each, might be considered shorter, more pleasant transitional seasons, times perhaps suitable for carefully planned outdoor activities, in protective gear of course, or specific religious celebrations, taking advantage of the extended twilight. While the equinox is the midpoint of the long day and long night, might be more somber occasions, perhaps focusing on community solidarity, resource management, and preparing psychologically for the arduous, unchanging period ahead. It's a fascinating thought experiment into how deeply our perception of time, our cultural rituals, our whole way of life are fundamentally tied to the specific astronomical environment we inhabit.
It really is. And then there's that truly bizarre phenomenon you mentioned earlier, the dead sun. That sounds particularly strange. What exactly is that again? And what kind of unique beliefs or practical challenges would it inspire among these hypothetical future colonists?
The dead sun phenomenon is one of the most unique and intriguing hypothetical aspects of experiencing Mercury's sky from the surface. It's a direct consequence of Mercury's eccentric orbit combined with its 3.2 spin-orbit resonance. During the part of its orbit when Mercury is closest to the sun, perihelion, its orbital velocity becomes so incredibly fast that it temporarily exceeds its rotational speed relative to the sun.
It's moving faster in orbit than it's spinning.
For a brief period, yes, from the perspective of the sun's apparent motion across Mercury's sky. For an observer standing on certain parts of Mercury's surface during this perihelion passage, the sun would appear to slow its movement across the sky, actually stop, move backward, westward for a while, stop again, and then resume its normal eastward motion.
The sun goes backward in the sky.
It appears to, yes. This period when the sun seems almost stationary overhead, or performs this little backward loop, is what one source termed the dead sun period. It would last for about 2 Earth weeks. And during this time, the sun would be at its absolute hottest and brightest in the Mercurian sky, casting almost no moving shadows. Due to the 3.2 resonance, any given location on Mercury, away from the poles, would experience this bizarre celestial event twice per Mercurian cycle, which is 176 Earth days.
That sounds utterly disorienting, maybe even terrifying. A sun that stops and glares down at you for 2 weeks. It must inspire some very unique beliefs and superstitions among colonists living under that sky.
Well, you can imagine it certainly would. The dead sun period would likely become deeply ingrained in the culture and folklore of any Mercurian settlement outside the polar regions. It would be seen as a time of extreme danger and perhaps supernatural significance. People would almost certainly stay indoors, deep within the radiation shielding of their underground habitats, or seeking refuge in the cool, permanently shadowed polar valleys if possible. Supplies would be rationed, movements meticulously scheduled to avoid any exposure to that relentless stationary glare. And the superstitions. One scenario imagines colonists whispering that if you listen closely during the dead sun, you can actually hear the voices of the dead, or perhaps even the sun itself speaking directly into your mind. Definitely. People might report experiencing bizarre happenings during this time, strange physical afflictions flaring up, unexplainable sightings of unknown entities or lights in the sky, mysterious voices echoing in their comm systems or their minds, disturbing or prophetic dreams becoming more common. It could even influence social customs. Perhaps some imagined future tribes or communities on Mercury might give children born during a dead sun period names like cursed, shadowborn, or ugly, stemming from a folk belief that they are somehow constitutionally weaker, or perhaps dangerously susceptible to paranormal influence or madness due to the intense solar energies present at the time of their birth.
But maybe others would see it differently, as a positive sign.
Exactly. On the flip side, other tribes or belief systems might consider birth under the dead sun a profoundly positive omen. Maybe they give names like Sol, Ra, or Sun-touched, believing the sun literally paused in its journey to specifically observe and bless their birth, perhaps granting them special extrasensory abilities, maybe linked to navigating Mercury's supposed quantum fields or ley lines in these fictional accounts. There might also be concepts like the dying sun, the period leading up to the dead sun, seen as a time of warning, a signal to prepare for the coming ordeal. And conversely, the dancing sun, the period immediately after the sun resumes its normal motion, signaling the dramatic end of the standstill, which would likely be a time for widespread relief, celebration, and rituals of cleansing or renewal. It truly highlights in a speculative way how extreme alien environments could profoundly shake human culture, folklore, spirituality, and our very perception of reality.
This incredible journey we've taken through Mercury's fiery past, its complex present, and its perhaps bizarrely imagined future as a human outpost. It brings us finally to its ultimate distant fate, billions of years from now. A dramatic and, it seems, inevitable end.
Indeed. Our sun, like all stars, isn't eternal. It has a finite life cycle, determined primarily by its mass and the amount of nuclear fuel it has available in its core. Right now, it's happily fusing hydrogen into helium, as it has been for about 4.6 billion years, and it has enough hydrogen fuel to continue doing so for roughly another 5 or 6 billion years.
And then what happens when the hydrogen runs out?
When the hydrogen fuel in the sun's core is exhausted, nuclear fusion there will cease. Without the outward pressure generated by fusion, the core will start to contract under its own gravity. This contraction will cause the core to heat up intensely. Eventually, it will become hot enough and dense enough to ignite a new round of nuclear reactions, fusing helium into heavier elements, primarily carbon and oxygen. This new phase of helium fusion in the core and hydrogen fusion continuing in a shell around the core will generate a tremendous amount of energy, far more than the sun produces now. This increased energy output will cause the sun's outer layers of gas to dramatically puff up, expanding outwards by hundreds of times its current diameter.
Hundreds of times, so it gets huge.
Enormous. The sun will transform into what astronomers call a red giant star. It will be much larger, much brighter, but its surface temperature will actually be cooler, giving it a reddish appearance, hence red giant.
Okay. And what does that mean for Mercury, the planet orbiting closest to it? What will be its ultimate fate in this red giant phase?
Its fate is sealed, unfortunately. The sun's expansion into a red giant will be so immense that its outer atmosphere will swell outwards and engulf the inner rocky planets. Scientists are highly confident, based on well-established models of stellar evolution, that Mercury and Venus will be completely swallowed by the expanding sun.
Swallowed whole, what happens then?
They will literally be vaporized. As they spiral into the sun's hot, diffuse outer layers, the intense heat will first melt their rocky surfaces, then evaporate them entirely, and finally their constituent atoms will just be absorbed and dispersed within the sun's convective envelope. They will cease to exist as distinct planets.
Gone. Just like that. What about Earth? Are we safe?
The fate of Earth is slightly less certain, as we reside right near the predicted edge of the sun's maximum expansion during the red giant phase. Early models suggested Earth might just barely escape being physically engulfed, though it would still be scorched beyond recognition. However, more recent, refined computer modeling, which takes into account more subtle effects like tidal interactions between the expanded sun and the planets and mass loss from the sun during this phase, suggests that Earth probably won't make it out intact either. The current consensus is leaning towards Earth likely being consumed as well, perhaps just before the sun reaches its maximum size.
So Mercury, Venus, probably Earth. All gone. What about Mars and the outer planets?
Mars might survive the physical engulfment, but it will be drastically heated. Even the outer planets, the gas and ice giants like Jupiter, Saturn, Uranus, and Neptune, while they won't be swallowed, will experience skyrocketing levels of energy and intense radiation pouring off the bloated red giant sun. Their atmospheres might be significantly altered, their moons potentially melted or evaporated. The entire solar system will be transformed into a vastly different and likely lifeless place compared to today.
It's a dramatic end.
It is. While we as a species will almost certainly be long gone by the time this happens billions of years from now, contemplating this distant future is a stark and powerful reminder of the dynamic, ever-evolving, and ultimately transient nature of our cosmos, our star, our planet, and everything within it. Nothing lasts forever on these cosmic timescales.
We've journeyed today through the truly astounding universe contained within the single name, Mercury. From its violent cosmic birth in a swirling nebula, its incredibly complex and extreme orbital dynamics, right through to its elusive chemical presence here on Earth, that strange liquid metal and its profound, sometimes tragic, sometimes strangely influential impact on our lives through ancient beliefs and modern markets. We've even ventured into its potential, perhaps far-fetched future as a human outpost before finally contemplating its ultimate distant demise, consumed at last by our aging sun. It really is incredible, isn't it, how one simple name can encompass so many different layers of scientific inquiry, cultural significance, and really profound questions about our place in the cosmos.
It highlights beautifully, I think, how knowledge from such diverse fields, bringing together astrophysics and chemistry, history and sociology, even finance and speculative futurism, how all these different ways of knowing can converge to create a much richer, more comprehensive, more nuanced understanding of even a single, seemingly simple topic like Mercury. The universe and our intricate interaction with it, both physically and culturally, is just far more interconnected and layered than we often realize day to day. It really invites us, doesn't it, to always try and look beyond the surface to see the connections.
A perfect note to end on. Thanks for listening to All in All.